Last time we started our discussion of non-abelian current algebras. And the framework we wanted to use is, instead of thinking of things, it's really just a notational change, but one that makes a lot of the discussion more transparent. Instead of thinking about in-states and out-states in an S matrix, we're just thinking about, for every incoming particle, we have some, for the nth incoming particle, or the kth incoming particle, we have some, we think of it as being created by some operator, OK of z, z bar, where z and z bar for a massless particle denote the location where it comes in on the sphere. And then there'll be various other quantum numbers which we'll suppress, and including the energy. And if the energy is positive, it's an incoming particle. If the energy is negative, it's an outgoing particle. So we're switching to a convention in contrast to what we were using in the earlier part of the class, where we were trying to emphasize the difference between how they appeared in the soft theorem for the incoming and the outgoing particles. We're now switching to a convention in which the sum of all the four momentum are 0 rather than the difference in the in and the out. OK. And the S matrix we're just going to write as a correlation function on the sphere. And if the total number of in and out particles are n, then we have n such insertions, where these can also be photons. And Lorentz transformations act on this in the usual way. Z goes to AZ plus B over CZ plus D, where AD minus B, they're complex numbers, where AD minus BC is equal to 1. OK, so that's how we're going to think about the S matrix. And then in that notation, we can write the soft theorem as O1. Well, the soft theorem would usually be written in terms of momenta. If you look it up in Weinberg's old paper, or Schwartz, or Weinberg, or whatever, it'd be written in terms of momenta, which we now think of as functions of z and z bar. Sorry, I meant to add here that if we want to have a massive particle, the operator which creates it won't be a local operator on the sphere, but it will have to be integrated over the sphere in a way that is we partially described in our discussion of massive particles. And can be worked out explicitly. So O1 of P1, which we think of as functions of z's, so we imagine we have n incoming plus outgoing particles, and then we add as an n plus first thing a gluon. And I'm talking about now non-abelian theories with massless gluons. I'm not Higgsing them, which depends on a momentum q and a polarization epsilon is equal to G, the Yang-Mills coupling G, times the sum over all particles, k equals 1 to n, pk, the momentum of the kth particle, contracted with the polarization of the soft gluon over pk dot q, the momentum of the soft photon dotted in with the momentum of the kth particle, and still inside the sum, but I ran out of room there, O1, P1, dot, dot, dot. And then when we get to the kth particle, we take the operator and act on it with the generator of the gauge group in the kth representation. So if this were a quark in the fundamental representation, this would be the generator in the fundamental representation. And the element in the Lie algebra would be the same one as the associated with the gluon insertion. So we have the sum of n terms, one by one, where, so it's unlike the soft photon theorem, where there was no insertion here. Or another way of saying it in the soft photon theorem, that since there was just a U1 charge, this just gave us the charge of the kth particle, and we could pull that out over here, and the whole thing was a soft factor. So this doesn't exactly relate the, if you insert the soft gluon, you don't exactly get back the S matrix element without the soft gluon insertion. It's slightly modified by color rotations of each particle one at a time. In other words, the soft factor is no longer just a number, and this is the general situation. It's only in very special situations that the soft factor is just a number that multiplies the matrix element. The more general situation is that it's an operator which acts on the S matrix element and changes the external states one at a time, and then you sum up all those terms. Okay. Now, we also defined last time, but let me just pause on that. This is just the standard soft gluon theorem. Let me just pause and ask if there are any questions about it before I go on. All right. So we also looked at the asymptotic behavior of the fields, and we saw that FUZ, the non-abelian field strength, had a leading term. We got too lazy to write the zero index here because there's too many indices floating around, so I'm just dropping it, is equal to du AZ, where again AZ is equal to AZA TA, where this would be the generator in the adjoint. And FZZ bar, on the other hand, which also has a leading order term of order 1, is DZ AZ bar minus DZ bar AZ minus I, the commutator in color space of AZ with AZ bar. And then we defined the analog of the soft photon operators, the soft gluon operators, one on scribe plus, which is du FUZ, which, with the boundary condition that AU goes to 0 at infinity, just becomes AZ at scribe plus plus minus AZ at scri plus minus. Now, so we can see just from this formula that whenever there's a soft photon present, whenever this integral is non-zero, AZ, it might be that in general we're going to, well, for now we're going to consider the case where the magnetic field strength is vanishing at infinity. That's not the most general situation, but it's what we're considering for now. So that would imply that this is AZ is a flat connection, but it might not be a trivial connection. And indeed, if FUZ is non-zero, it can't be a trivial connection at both the top and the bottom of scri. All right. So, and then we also defined an NZ on scri minus, which was minus infinity to infinity du. And by the way, I'm only integrating over u, not z and z bar. So this is some one form on the sphere. dv fvz, which again would be az evaluated at scri minus plus minus az at scri minus minus. And finally, we defined, for future use, a current Jz is minus 4 pi over the square of the Yang-Mills coupling of Nz minus Mz. Okay, and we also noted that this whole setup with the boundary conditions that we've chosen is invariant under large gauge transformations of the form epsilon of zz bar generated by epsilon of zz bar at scri plus minus is equal to epsilon of zz bar at scri minus plus, and a bang du epsilon equals dv epsilon equals 0. So just like the Abelian case, except that now everything is a matrix, yes?
That mz should be n minus.
N minus c. Okay. So that's basically all from last time. And now I'm going to start new stuff. But are there any questions? Okay. So now we can take this. So I'm not going to go through all this again. But it works out the same as before. You can take these things, which involve integrals over retarded times, and you can rewrite them in terms of creation and annihilation operators of, here we have a gluon, the operator which creates a gluon. I forgot that, and this is, we're taking q to be small, so this is plus order q to the 0. This has a pole in q, and then there's a finite p. So this is not the whole expression. So so as before, we can take this OA, and here the A index has disappeared because I'm contracted with the generator T in this point to get a more, at this point, to get a more streamlined notation. Formulas are already pretty long. And so everything on this board is an n by n matrix if we're doing UN or SUN. And we can take this O and we can turn it into, or we can take a combination of these O's going to, with Q going to 0. If Q goes to 0 from on top, we get that corresponds to an outgoing thing on scry plus. If it goes to 0 from below, we get an incoming thing on scry minus. So we can take a combination of these things and make up this JZ. And then we can take all the P's in here and use our famous formula for trading P's for Z's. And we can also, for ZKs, PKs for ZKs, and Q for Z. And after algebra, which is very similar to the algebra that you did in the U1 case, after a couple pages, you can rewrite this formula, the soft photon theorem, in the following very pretty way. I'm going to put the A index back in. J A Z O1 is equal to, and then I need to emphasize, I meant to emphasize here, something that should be but isn't usually emphasized in textbooks, is that we're assuming that the sphere at infinity has a flat connection on it, U equals 1. In other words, if we have a gluon of one color and an anti-gluon of the same color, those things make up a color singlet. If you have that even if one is going out of the North Pole and one is going, like if you have a red quark, I could talk about quarks. If we have a red quark going out the North Pole and a red anti-quark going out the South Pole, that is a color singlet. And that, of course, only makes sense if you can compare things at different points on the sphere. And you can only compare things at different points on the sphere if you have a UN. Let me assume the gauge group is UN. If you have a UN connection that enables you to transport them, put them next to each other, and see if they make a singlet. So that is always assumed here. But already here, we see that that assumption is a little bit funny, because when there's soft gluons around, we have to be careful about what that means, because when there's soft gluons around, you change from one flat connection. They characterize transitions from one flat connection to another flat connection. So we're going to need to be discussing the case where there are different inequivalent flat connections. Okay, so at U equals 1 is equal to, looks just like the electromagnetic formula, the sum from k equals 1 to n, 1 over z minus zk, O1 T AK OK dot 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 ON. Okay, so I've chosen my normalization of J to make this formula as simple as possible, and to eliminate the factors of G Yang-Mills squared and pi and so on. Now, and this is also at U equals 1. Now, anybody who's studied two-dimensional conformal field theory will certainly recognize this formula. It's the formula for the insertion of a UN Kac-Moody current into a correlation function of a two-dimensional conformal field theory in which the OKs, the operator insertions transform under the kth representation of the whatever the Kac-Moody group, well, let's just say SUN. Okay, so it's a very familiar looking formula. And I think that this way of looking at things is much more natural than this way of looking at things, that this is a nicer way to write this formula. And I think it's even nicer than the way we were writing it before, where we were talking about ingoing and outgoing states and charges that acted on ingoing. And it captures the same information, but I think in a nicer way that can lead to further insights. Now let's take both sides of this, and now let's pick a contour, an arbitrary, yes?
So this formula is only true for the two-dimensional language, only true for OI being primary of the Kac-Moody algebra, right? How does that assumption coming from the four-dimensional
Yeah, that's a good question. Where is that assumption coming? I guess we're assuming that wait, what are you imagining now? That if we take descendants of OK, oh, the point is that the level of J is 0. I think the corrections you're talking about will involve the level of J.
Oh, that J is J0.
No, it's not J0,
Oh,
but
I mean the level of the Kac-Moody algebra.
the level of this Kac-Moody algebra is 0.
But still, if OI were not primary, wouldn't I expect like other terms when I'm?
I don't think so. No. No, there's secretly a second current algebra in here which we don't fully understand. Let me just make the side comment that we could make a second, we could bosonize the charge of these things and then take their derivatives. This is kind of a technical comment, but we could take their derivatives and that would give us a second current. And that would have a level with this. And then there would be some more complicated set of word identities that we don't understand at this point.
But I thought here we are just using the fact that JOOPE has singularity 1 over Z times this T matrix acting on O.
Right.
And if O is not a primary, that might not hold.
You mean, okay, but it's also true that JA, didn't write it, but it's also true that JA, it's a homework problem, that JAZJW does not have a pole.
JJOB has a 1 over Z pole with coefficient being J, right?
Sorry, it has a 1 over Z minus W FABC, but it doesn't have a 1 over Z minus W squared in it, with a K in it.
Sure, if K, okay. But here we only have one J, right? So I thought in the equations you wrote, it's more about the JO.
Right. So suppose O is a primary, and then you could make J descendants.
Oh.
Okay. But those J descendants are going to transform in the same way. This formula is still going to be true because there's no level in the JJOPE. No. There is a second Kac-Moody, which I'm not going to talk about, because we haven't worked out how to think about it yet, which will bring in a level and some more interesting and complicated structure. But I'm telling you now what I know to be correct.
Did you explain why the level is 0? Or not yet? Or
Well, it's just the statement that it's the homework problem.
oh, sorry, I didn't take this one.
Okay. Well, we just assigned it, I guess.
Okay.
Or did we just assign? It's out already? Yeah. It's just you compute a correlation function with two j's, and you take the double soft limit, and you see if there's a double pole, and there isn't. Okay. Though I should add that unlike in the abelian case, this has corrections. This was a comment I was going to make later, but let me make it now, since you've asked about the level. Unlike in the abelian case, the soft gluon theorem, the soft photon theorem has no loop corrections. It's an exact statement to all orders in perturbation theory. And I conjectured that when you add the magnetic stuff, then you have a non-perturbatively exact formula. Didn't prove that, but there doesn't seem to be much room for correcting that formula. And but the soft gluon theorem does get corrections at one loop. And so what I'm doing here is really tree level. And so it's a very interesting unsolved problem to understand what those loop corrections mean in this language. And Burkhardt, who's not here, some other people were trying to relate that to a level. So it could be that at the loop level, when loop corrections are included, there's some kind of level here. But this is all unexplored territory.
Do we expect the level to be positive or negative?
We don't even know if there is a level, and we don't know whether to expect it to be positive or negative.
Or do we expect the boundary CFT to be unitary? Or?
I don't think there's any reason to expect that the boundary CFT should be unitary. Okay. So all right, so the next thing I want to do is simply to take both sides of this formula and multiply it by epsilon A and integrate over some arbitrary contour C in the sphere. The arbitrary contour C in the sphere. And now I take integral dz over 2 pi I of jz O1 to On. And now we integrate the right-hand side. And what we get is a sum of all contours that are in C. The sum over all k's where zk is inside C of O1 epsilon k OK to ON. Again, this is at u equals 1, at u equals 1. And where epsilon k is equal to epsilon a t a k. And I needed an epsilon here, and I needed a trace. Okay, so now, it might have bothered you. It's a contour in a sphere. How do I decide what the inside and the outside is? Well, the point is it doesn't matter, because if I were to unrestrict the sum here, then I would just have a gauge transformation, a global gauge transformation of the whole thing, and that would be 0 just by the statement that the whole thing has to contain a singlet. The whole thing has to be a singlet. The correlation function, the S matrix vanishes unless the whole thing is a singlet. Okay. Now, so any questions about this? Now let's consider what happens if this u is 1 plus I. In general, we can consider u going away from, we can consider any flat connection on the sphere. So the connection will be u inverse AZ will be u inverse DZU. So we have a flat connection on the sphere, which if it's near 1, we can expand like this, where epsilon is in the adjoint. And we can write, let's choose the epsilon so that epsilon is equal to epsilon A inside C, and it's equal to 0 outside C. So let me just draw a picture of this. Here's my sphere, S2. Here's my contour C. Here I have some non-zero epsilon A. Here I have epsilon A equals 0. And here I have some operator insertions which lie inside the contour, and there are also some that lie outside the contour. So this is the K inside, K in C. Okay, so suppose I do a gauge transformation of this correlation function O1 to ON with a gauge parameter u equals 1. So I do an infinitesimal gauge transformation. That is, by that I mean evaluate it at u equals 1 plus I epsilon, subtract from that the value at u equals 1. Well, what is that going to do? Well, that's going to infinitesimally transform every operator that lies inside the contour, because my gauge parameter is only non-zero inside the contour. So this is just equal to I times, because of the I there, the sum of K in C of O1 epsilon K OK ON u equals 1 which of course is just equal to what I wrote up there, integral dz over 2 pi, canceling the I, trace epsilon jz O1 to On u equals 1. So we can characterize this by saying that integral dz over 2 pi I of trace epsilon jz is equal to the integral over the region inside the contour of d squared z gamma z z bar delta u ac epsilon delta u a epsilon a. In other words, if I integrate j around a contour, that is equal to that insertions of integrals j around the contour c weighted by epsilon generates large gauge transformations on the boundary. They are the infinitesimal generators of large gauge transformations on the boundary, which are characterized by this flat connection U. Any questions about that? Okay, now I could have done something more general. I could have, up here, I didn't need to take epsilon to be a constant. I could have taken epsilon to be any function of z. And then I but if I have any function of z on a contour C, I can always extend that holomorphically into the interior. There's always some function inside C that I can, a holomorphic function with no poles inside C that will agree with epsilon on the boundary. So this equation will remain true if I integrate it. I can, a more general equation, which epsilon is a function of z, and then I can generate arbitrary holomorphic gauge transformations, holomorphic large gauge transformations inside this boundary. So J is really the generator of holomorphic large gauge transformations. Now, of course, we're on a sphere here, so if there are no poles inside this curve, there's certainly going to be poles outside. So if I redefine what I mean by outside and inside, when I try to contract this on the other side, I'll run into poles. There'll be residues there where I will have extra insertions of Jz. In other words, extra soft graviton insertions. And in that way, I will get another, I'll get another true relationship, which will involve some sum of soft graviton another correct relationship, which will involve some soft graviton insertions along with gauge transformations in the region outside of C. Okay. So any questions about that? So now, now we could have also formulated this in the way that we talked about QED. We could have defined a charge Q plus epsilon is equal to 1 over g squared Yang-Mills, integral over scribe plus minus, the dual now of trace epsilon f, where this is now the full non-abelian field strength, which actually, though, I think if you work out the expansion, it's just FUR. It doesn't have any non-abelian. The leading term at large R doesn't have any. Oh, no, it has an A. It's DUAR plus AU. We did that last time. So, and by the usual antipodal matching conditions at infinity, this will equal Q minus epsilon. And if we integrate this by parts now, it's just like before. We integrate by parts and write it as an integral over scribe plus. And we'll get one term that's d epsilon that will be linear in the gauge field. That will give us something like n. And so that will be a soft term. So we'll have a soft term. And then we'll get a hard term also. And the hard term, there will also be here terms which will be quadratic in the, because in non-abelian theories, the gluons themselves carry charge. So the constraint equation will relate the derivatives of these terms to the non-abelian color current carried by the gluons going through scry. So we'll also have a hard term. And similarly, we'll have a soft and a hard piece of the charge on scry minus. Now, this JZ generates transformations on anything that's inside the contour C. So it's reformulating things in a slightly different way, in a sort of more democratic way. And it will generate transformations on anything inside the contour C. And things which, in this notation, things which are coming from scry minus or going out to scry plus are differentiated only in the sign of their energy. So they can be inside this contour C if they're from scry plus or from scry minus, and they will be acted on by this JZ. So now I want you to, I'm going to give you 2 minutes to think about this. I want you to write a formula for integral over the contour C of trace epsilon jz over 2 pi I. What is that equal to in terms of things that I've written on this board? So the answer is very simple, but it's a little confusing at first, so it's good for you to minus epsilon, sorry, this would be out and this would be in, equals to 0. And this generated two kinds of, it generated gauge transformations, but there were two pieces, the soft piece and the hard piece. And in this kind of formula, what we've done is we've rewritten it by taking the soft pieces and putting them on the left, and the right-hand side is just the generator of the gauge transformation on the hard pieces on the O's. So, and this formula will be true if this epsilon is a constant. This epsilon must be, this left-hand side only needs the value of epsilon on the curve, which if we take it to be a constant, on the right-hand side, this epsilon, this involves an integral over the sphere, but the epsilon will be a constant everywhere inside whatever this contour is. That's the epsilon that you must choose in order for this equation to be correct. If we have a more general epsilon, there still is an equation of this type which is correct, where the epsilon is non-zero inside the disk whose boundary is C. It's holomorphic, and its boundary value on C agrees with the epsilon here. Okay. So that is the relationship between this sort of Kac-Moody algebra way of thinking about things and the old way of thinking about things in terms of in and out Hilbert spaces. Okay, so I'm about to go on to gravity finally, but I have some just comments I want to make about this. I've sort of things I've said, but I want to stress. First of all, the solution of already the classical, even before we get to quantum, the solution, to get the solution of the classical scattering problem, using the equations of motion to get F is simply not enough. So if we have Minkowski space and we're given F everywhere in Minkowski space, the non-abelian field strength, that is not a solution of the scattering problem. A solution of the scattering problem requires that you know AZ on scri minus and AZ on is a map for some classical solution of the Yang-Mills constraint equations on scri minus to outgoing Yang-Mills equation on scri plus, and that had better include AZ. And the necessity of including the potential and not just the field strength is more evident in the non-abelian setting than it was in the abelian setting. Because in the abelian setting, if you did a gauge transformation, all you do, U1 gauge transformation, it doesn't act on the electromagnetic field. It only acts on charged excitations, and all it does to them is give them a quantum mechanical phase, and you have to do some quantum mechanical experiment to to determine if the phases are the same or not. So the necessity of knowing the potential rather than just the field strength in the Abelian theory is really only very apparent at the quantum level. Here already at the classical level, in classical non-Abelian gauge theory, we certainly know whether something is in a color singlet state or not. So will certainly be a physical question, and we can't know that unless we can compare things at different sides of the sphere, and comparing them at different sides of the sphere requires even if the field strength vanishes infinity, there still in general will be a flat connection, and we'll have to be able to parallel transport around the sphere. And so there, again, as in the Abelian case, there are an infinity of vacua, which we can classically think of as being characterized by flat connection on the sphere, or quantum mechanically we can think of going from one vacuum to the other by adding soft gluons. I won't repeat that story all over again, but again, the soft gluons, the symmetry that we're talking about here is spontaneously broken, just like in the U1 case, and the soft gluons are the Goldstone bosons of that spontaneous symmetry breaking. So if we just had F, we wouldn't have a solution of the equation of motion, because given one F, we could do a gauge transformation up here. Given one F that solves it, we could do some gauge transformation up here, and we would have another F that solves it. So we have to supplement it with this boundary condition that AZ at scri plus minus is equal to AZ at scri minus plus. In other words, the scattering problem is not defined without specifying how the fields are matched up at spatial infinity. And you might ask how people have gotten away for studying non-Abelian gauge theories for over half a century without ever saying this. Well, this rule is implicit in Feynman diagrams, where all the propagators in the Feynman propagators obey, effectively give you things which implicitly invoke this boundary condition. Now, one of the interesting things about so now let me end with a rather, well, conclude this little discussion with an inconclusive comment. One of the things that you often read is that there is no definition of the S matrix in non-Abelian gauge theory. Now, the precise words that you hear is that one often hears the phrase, the S matrix doesn't exist in non-Abelian gauge theory. I don't think that statement is correct. I think the correct statement is there's been no construction of an S matrix in non-Abelian gauge theory. Nobody even really tried to show that there was no way to define an S matrix. The usual tricks that worked in other cases didn't work in non-Abelian gauge theories, and more specifically, there's also the origin of the problem is this infrared divergence, which is precisely brought about by these soft photons and gluons that we've been discussing. Now, the soft photons are also there in QED, and they create divergences in the S matrix which are canceled by zeros. So the naive thing that you would do to construct an S matrix in QED doesn't work. But there's a more elaborate construction, which I definitely won't go into and don't understand very well myself. In fact, I'm not persuaded that anybody actually really does understand it. But there's something called the Fadeev-Kulish construction, which all textbooks in quantum field theory footnote, and I'm not sure that the writers of those textbooks have read the paper, but they all footnote this thing that you can use the Fadeev-Kulish construction and you can get a finite an S matrix for QED, which is free of infrared divergences. And so people somehow feel that the problem of infrared divergences in QED has been dealt with in that way. People tried to use the Fadeev-Kulish type approach for non-abelian theories, and it just got too complicated and people gave up. Now, there's something else that is done about infrared divergences, which is people put in an infrared cutoff, compute inclusive cross-sections, which are not S matrices, they're probabilities, and show that they're finite. And that's a perfectly fine procedure if your goal is to compute cross-sections at the LHC, where there is a real physical cutoff and what kind of wavelengths you can measure. But if you want to understand the basic structures about quantum field theory, one of the most basic questions you could ask, which is what we're asking now, is what are the symmetries of the S matrix? The first thing you need is an S matrix. There aren't symmetries of inclusive cross-sections or probability amplitudes. Even energy conservation is not a symmetry of those things. So if you want to talk about symmetries of the S matrix, you need an S matrix. People have barely succeeded in defining an S matrix for QED. The tricks that were used for and also for quantum, it's claimed that the same tricks work for quantum gravity, but not for non-abelian gauge theories. And the basic reason for that, why non-abelian gauge theories are different from gravity and QED, is that the problems that we're talking about here are problems at very long distances. The issues are at very long distances at infinity. And there's a sense in which in both quantum electrodynamics and in gravity, at very long distances, there's no interactions and you have free field theory. The same thing is not true in non-abelian gauge theories, like, for example, n=4 Yang-Mills theory. There are interactions which persist and must be dealt with at arbitrarily long distances. Now, all this discussion over the last 50 years has taken about the infrared nature of quantum electrodynamics and non-abelian gauge theories has taken place in the absence of any knowledge of the infinite number of symmetries that govern precisely that sector of the theory. And so the hope would be that by through some kind of understanding of this symmetry, there may be some way to define an S matrix and or some generalization of an S matrix, or in other words, some object, some exact object in the quantum theory. The relationships that I'm writing down here, because of these infrared issues, are really only valid in non-abelian theory at tree level. And so the conjecture would be that there's some kind of object that relations like this is an exact object in the non-perturbative theory, that relations relations like this apply to. Any questions about that? Okay. Now, let's see. I guess some more comments here. There's a magnetic generalization of this. It's obvious that we would also get more conserved charges if we didn't have the star there. That also hasn't really been worked out. And there's the question of the level of this current algebra, which also hasn't been worked out. There's also the question of soft limits. Now, in the homework, we talk about the double soft limit of two JZs, but there's also an issue about the double soft limit of a JZ and a JZ bar. And that turns out to, that soft limit turns out not to commute, and that's indicative of some more structure that we haven't fully understood. There are comments about it in some papers. As I said, there are loop corrections. And then finally, I want to mention that both in QED and here, there are subleading soft theorems, which will have more corrections. They're corrected already in QED. They'll have corrections here, which these order Q to the 0 pieces, which I guess I've erased, also have universal features and are related to symmetries. OK, so that concludes everything we have to say about symmetries, asymptotic symmetries, soft theorems. Maybe we'll come back and say a little bit more about memory effects later in abelian and non-abelian gauge theories. And we're about to move on to the very interesting case of gravity. But let me pause for questions, if there are any. OK. OK, so we've written down a formula for the metric in Minkowski space in retarded coordinates. Plus GAB dxa dxb. And if this is round metric on the two-sphere, then this would be the flat metric in Minkowski space. Now we want to go to gravity, which means that we're interested in more general metrics, not just the flat metric. And the first statement I want to make is, so we could have much more general metrics, but we're going to work in a particular coordinate system. And in general, any Lorentzian metric can locally be written in the following Bondi form. So we put an arbitrary function u here, traditionally called u there. We put an arbitrary function traditionally called e to the 2 beta here. GAB is an arbitrary 2 by 2 matrix. And we add here plus a half UA du, and then dxb plus a half ub du. So notice that this metric has no, we have set here GRA. So A goes from 1 to 2. We've set GRA equal to 0. And we've also set RR equal to 0. That's 3 local conditions. In general, diffeomorphisms are parameterized by a 4 vector, so we get to impose 4 local conditions. And so the 4th condition that we're going to impose is dr times the determinant of the 2 by 2 metric GAB over r squared is equal to a constant. Is equal to 0, sorry. So this is independent of r. So in Minkowski space, the determinant of GAB, and this is true at every point, at every angle on the sphere and whatever. So in Minkowski space, the determinant of the 2 by 2 metric on this sphere would just be r squared. So this would be 1, and we would have dr of 1 is.
I think the 1 over r squared should be inside the determinant.
Yeah. So r, let me call it r to the 4th. So, okay, now, and probably we want to think of A, we're going to think of A and B as being Z and Z bar. So A and B, X, the two X's are Z and Z bar. Now, the first question you might ask is why do I want to use these coordinates? Well, these coordinates were introduced, I believe, by Bondi, or at least I've gotten in the habit of calling them Bondi coordinates, something like 1960. And something like more than half of the literature on asymptotically flat spacetimes in general relativity is written in these coordinates. So I don't actually think they're a particularly nice set of coordinates. I think it's kind of nicer to, instead of imposing this condition, to set this to 1. That's a different coordinate system. You could do that. But then you can't look things up in the literature for a so most papers are written up, so I'm not going to, you should get the same results no matter what coordinate system you use. But as we're going to discover, and this is why I did the gauge theory case first, already so far we've had a lot of long formulas. And when you go to gravity, somehow they get exponentially longer. And so it's very nice to be able to look up some of those exponentially longer formulas in other people's papers rather than having to work them all out yourself. So I'm going to continue in the spirit of the last half century in using these Bondi coordinates. All right. So so far, I haven't imposed any conditions on the geometry. Locally, any geometry Lorentzian geometry can be written in this form. But now I want to talk about geometries which are asymptotically flat. And in particular, I want them to be flat at r goes to infinity at fixed u, z, and z bar. So that is, we're going to talk about geometries that are flat near future null infinity. And there was much discussion, especially in the 60s, of what constitutes an asymptotically flat geometry. Physically, and I don't think that there were different proposals, and in fact, one of the main things, it's not like a box where you can, well, suppose you want to study a scalar field in a box. You get to choose whether you Dirichlet or Neumann boundary conditions. But you can get in trouble there. You can't choose Dirichlet and Neumann, right? If you study a scalar field in a box and you impose Dirichlet and Neumann boundary conditions, there will be no solutions. So you have to do something consistent. At future null infinity, it's even much more subtle than that. You want to choose your behavior up there. It's not as if you're reflecting some excitations off of future null infinity. You start somewhere in the middle, stuff boils off, radiation goes up to null infinity, and you have to know what kind of behaviors you would typically get. And it turns out, actually, that the whole school of relativity, starting from the 60s up until the work of Christodoulou and Kleinerman in the 90s, had it wrong in a very important way. And but the piece I'm going to tell you about, they had it wrong as far as how things behaved at scri++ and scri plus minus. But they did have, so we'll come to that later, and it will be important later. And but for now, I'm just going to talk about what happens not at the edges of null infinity, but in the middle of null infinity. And later on, the edges of null infinity, when we want to discuss it, will become important. But the fact that all of these people had it wrong for so many years, illustrates that there is no really systematic way of deciding what these boundary conditions. Well, maybe there is, and maybe Christodoulou and Kleinerman finally solved it. Okay, so what asymptotically flat means is that at generic points in the middle of scri, ds squared should go like minus du squared minus 2 du dr plus 2 times something called the Bondi mass aspect over r du squared plus, sorry, I didn't mean to write it like that. So we start out with minus du squared minus 2 du dr plus 2r squared gamma z bar dz dz bar, where gamma z bar is the same thing it's the round metric on the unit 2 sphere. So this is the leading term at large R. This is flat space. This is flat Minkowski space. And now we're going to add corrections. Now the corrections aren't necessarily going to be all of order 1 over R, because you see the leading term here is already of order R squared. So what do the corrections look like? Well, there's a correction to this coefficient, which is proportional to the so-called Bondi mass aspect, 2mb over r du squared. And then there's a term that looks like plus r, which belongs in here. It's plus r CZZ dz squared. But this affects only the metric on the two-sphere, and it's subleading relative to this term here, because there's only one r. This is r squared. So to leading order at large r, the sphere, the metric on the sphere, is still round. So the metric on the sphere is round plus order 1 over r corrections, which are given by r, which this CZZ is completely arbitrary. And then we have plus the complex conjugate, r CZ, metric has to be real, of course, dz bar squared. And then we have plus uz du dz. That's these cross terms here, plus uz bar du dz bar. And then there's more terms that continue with this expansion, which are not completely arbitrary. So for example, if you compute the determinant, if you look at this equation here, you will find that it does not, that the terms that I've written here will not satisfy this equation. I'll have to have a further subleading in r term. In fact, I'll need a term proportional to c squared dz dz bar in order to satisfy this. So there's subleading terms with, further subleading terms with some structure in them, which is, discussed in the literature, including in Bondi, Mesner, and Sachs, which is part of the assigned reading. But we're not really going to care about those. The subleading terms aren't going to affect us. All we need to know is that that we can complete the metric in a way that satisfies all these conditions. Now, one important thing that you're going to do in a homework problem is to see, we want to say that the Riemann tensor in a local orthonormal frame falls off like some power of r. What is it? 1 over r squared in an orthonormal? Yeah, I think it's 1 over r squared in a local orthonormal frame. And that requires that uz is related to cz by this relationship where dz is the covariant derivative, not with respect to the two-dimensional metric g, but with respect to gamma zz bar. It's the covariant derivative on the unit 2-sphere. And the index on it is raised, again, with gamma zz bar. So that's a homework problem to show that uz asymptotic flatness requires that uz is equal to dzz bar. So then, in addition, so asymptotic flatness then is that GUU is equal to the general statement of it, which has many variations, but this is the basic idea in different treatments in the literature. GUU is -1 plus order 1 over r. That is, it's this Minkowski value plus a 1 over r correction, which we're characterizing by m Bondi mass over r. And then GUR is equal to -1 plus order 1 over r squared. GUZ is order 1. That's the UZ And then GZZ bar is R squared gamma ZZ bar plus order R. And GZZ is order R. And GRR and GRZ are 0. So this defines, or this is how Bondi, Metzner, and Sachs defined an asymptotically flat metric. And the most important feature of this definition is that it allows for gravitational waves. Right? It's weak enough so that gravitational waves can pass through null infinity. Now, so far, I haven't said in this discussion the word the Einstein equation. I haven't imposed any equation, including the constraint equations. This is just the statement about metrics that at very late retarded times at null infinity are flat. So we can describe them in this way. And as I said, we have to stop a little early. But so next time when we start up again, we'll talk about what structures and what relationships there are between these various quantities that are imposed by the Einstein equation. And then we'll go on to analyze, following Bondi, Metzner, and Sachs, what the asymptotic symmetries are of this these kinds of geometries.